Okay, Ji. Today we shall discuss the process of osmosis. As in previous discussion, we had a detailed discussion about various other mechanisms in the body
Yes. जीएल करने उन्हें लिंक शेयर कर दी है.
which were involved in movement of different types of the molecules. For example, we have discussed about the movements of the lipid soluble molecule. As you know that they can easily move through the lipid bilayer of the membrane. Similarly, we have discussed about the movement of the ions, as the ions can move through the ion. Discuss about the movement of the polar molecules. For example, we have glucose and various other molecules, and we have discussed that those molecules can move through the help of transporter proteins or the carrier proteins, which is called facilitated diffusion, or in some cases when the movement is from lower concentration to the higher concentration, in that case it will be called as active transport. So as far as the movement of the water molecule is concerned, as all of you know that major portion of the plasma membrane is made up of lipid bilayer, and that is hydrophobic. So water, because of its polar nature, water will not diffuse through the lipid bilayer. So how the movement of the water molecule, as water is very much necessary component for the survival of the cell, for the proper functioning of the cell. So how the movement of the water molecule will be accomplished across a membrane. So as you know that water is polar molecule, and if we talk about the structure of the water molecule, it is about 0.3 nanometer in diameter. So it will diffuse across the membrane very rapidly, but because of the polar structure, water will not be able to penetrate the non-polar or lipid bilayer region of the plasma membrane. And if we take an artificial phospho lipid bilayer, and we study the permeability of the water to some extent, that artificial lipid bilayer is G. Yes.
स्लाइड नहीं शो हो रही, किसी को भी नहीं शो हो रही स्लाइड.
Okay.
हो रही है ना?
Now, can you see the slide now?
Yes sir.
Turn your screen now.
No sir, मुझे हो रही है शो.
किसी को भी नहीं हो रही?
सर हो रही है शो. सर हो रही है.
Okay. If we take artificial phospholipid bilayer and we examine the permeability of the water, it will show some sort of permeability. So it means that water can diffuse through these small channels or small areas, at least to some extent, although majorly the membrane is made up of lipid bilayer. So when we talk about the natural membrane, plasma membrane, natural membrane is having the permeability to water that is 10 times greater or higher than that of the artificial lipid bilayer. So what will be the mechanism for the movement of these water molecule? So a group of the membrane proteins which are present on the surface of the plasma membrane, and those will be present on the surface of natural plasma membrane. Those group of the proteins are called as aquaporins. So these are the areas, these are the portions, these are the proteins. They form the channels, and through those channels water molecules can diffuse across the membrane rapidly. So concentration of the water channel, the aquaporins, that is different in different membranes, and in some cells, for example, number of the aquaporin channels or the protein, they actually determine the permeability of those membrane to the water molecule. Mean if the membrane is having large number of these aquaporins are the channels, then it means that that membrane will be showing large permeability to the water movement as well. And similarly, the permeability can also be altered with the help of certain types of the signals. Certain type of the stimulants are the inhibitors. They can alter the permeability of the membrane to the water molecule. So this net diffusion of the water across the membrane with the help of these channel proteins or the porins, aquaporins, will be called as osmosis. And as in case of diffusion, for the water to move across a membrane, there should also be a concentration gradient of the water. Mean there should be difference of the concentration of the water on the two sides of the membrane. That's how the net flux will be built and the movement of the water is possible. So difference in concentration of the water, how that difference can be maintained, can be established across a membrane. So when we add any solute to water, molecules of the or a solution of the water, it means that the concentration of the water will be lower or will decrease by the addition of the solute particle. And when the concentration of that water is compared with the solution of the pure water will have high concentration of the water as compared to one in which the solute is added. For example, if we take glucose as a solute and we dissolve this glucose in the water, so concentration of the water in the solution which is also having the glucose molecule will be lower as compared to one solution in which we have pure water. So the volume of the glucose which was added to the solution, to the water solution or the pure solution of the water will automatically decrease the concentration of the water, and it will decrease pure water molecule. For example, if we add 2 molecules of the glucose, so it means it will lower the concentration of the pure water by 2 molecules. So equal volume of the pure water or equal number of the molecules of the pure water, they will be decreased by the addition of the glucose molecule, because the glucose molecule will occupy the same space as that was occupied by the water molecule in pure solution. So if we take this in quantitative terms, for example, a liter of the pure water, the weight of that liter will be 1000 gram, and the molecular weight of the water, as all of you know, that is 18. And if we want to calculate the concentration of the water in pure water, you can simply calculate the concentration of the or molarity of the water. Mean 1 molar solution of the water we can calculate by dividing the molecular weight of the water with the pure volume of the water in one solution, or the weight of the volume in 1 liter of the solution. So that's how 55.5 is the concentration of the water in pure water solution. This is 1 molar solution of the water. You can also call it as 1 molar water solution, or the pure water solution. So when we will add the glucose molecule, definitely it will decrease the water concentration, and this decrease in the water concentration, it will be approximately equal to the concentration of the added solute. 1 solute molecule, simply you can understand this as that 1 solute molecules which is added to the solution will displace 1 water molecule, and water concentration in a 1 molar glucose solution is therefore it will be 54.5. Mean when 1 molecule of the glucose was added to the pure water solution, this 1 molecule of glucose will decrease the concentration of the pure water solution by 1 molecule. Now the concentration of this water solution will be concentration of the water in this solution will be 54.5 mole. rather than the 55.5, which was the concentration of the water in pure solution before the addition of the glucose molecule. So when we will add water to the solution, definitely it will dilute the solution, and similarly when we will add the solute, it will also dilute the water. So both water as well as solute, they can dilute each other. Their solution can be diluted. So when we will increase the concentration of the solute, the greater the solute concentration, it will automatically lower the water concentration. Mean increase in solute concentration will decrease the water concentration in a solution. So it is also very much important to understand the point that degree to which the water concentration is decreased, that how much water concentration is decreased in a solution when we add a specific type of the solute. It is dependent upon various factors. The first important factor is solute. It is dependent upon the number of the particles. Molecules are the ions of solute in solution. Mean if we add a huge number of the solute, it means the concentration of the water will be decreased to larger extent, on a larger scale. But if we add a few molecules of the solute, there will be minute decrease in the water concentration. So the first important thing is number of the solute molecules which are added, either they are ions, they are molecules which are added in the water. And similarly, if we talk about the chemical nature, chemical nature will not have any effect on the water concentration when we add any type of the solute particle. For example, here we take an example. We have one molecule of the glucose in 1 liter of the solution. This is solute, and this is water. So when we add one molecule of the glucose in 1 liter of the solution, it will decrease the water concentration by the same extent as one molecule of an amino acid, or one molecule of urea, or one molecule of any other molecule that exists as a single particle in a solution. Mean it is the number of the solute molecules which are being added to the solution rather than their chemical composition. No matter the molecule is ammonia, molecule is glucose, it is amino acid, all of them, if their number is equal, they will have same effect on decreasing the concentration of the water in a solution. So here in this example, we have solute, and the concentration of the solute is 2 osmol, and we have water. The concentration of the water is 53.5 molar. This is the concentration of the water. And in the compartment 2, we have solute concentration is 4 osmol, and we have water concentration is 51.5 osmol, or 1 liter. So between two compartments are of equal volume. These are the two compartments of equal volume. This is compartment 1 and this is compartment 2. So from this compartment, when the two molecules of the solute, they will move to the compartment 2. Here we are now. This is the initial concentration, and this is the equilibrium stage. When the equilibrium stage is reached, it means both of our component. If we add these two concentration, this is 2 and 4. 2 and 4 mean the total concentration is 6. Total concentration of the solute is 6, and similarly, it should be equal to 55. So this is the total concentration, or it is equal to, when we take it in combined form, it will be around about 105. But if we talk about this compartment individually and this compartment separately as well, at the equilibrium stage, one molecule of the solute will move from this compartment 2 to compartment 1, and hence the concentration of the solute will be increased. Now it will be 3 osmol here at the in the compartment 1 as well as 3 osmol in the compartment 2. So it means the solute is having higher concentration initially in the compartment 2 and having lower concentration in the compartment 1. So as following the principle of diffusion, in case of osmosis, the solute particles, they will also move from their higher concentration to their lower concentration. So solute will move from compartment 2 to compartment 1, and this movement will continue unless until two compartments will have the equal concentration of the solute particle, and equal concentration will be 3 osmol. Now at this time, at this equilibrium stage, there is no net movement. Means both the compartment, they will have the same concentration of the solute and same concentration of the water as well. So initially compartment 2 was having higher concentration of the solute, so solute will move from compartment 2 to compartment 1. And when we talk about the water, initially the water concentration in this solution is high in compartment 1, and water concentration is here is low. So water will move from its higher concentration to lower concentration, and this movement will continue unless until the two compartments, they are having equal water concentration, which is 52.5 in both cases. So this is the when the equilibrium stage is reached, no further movement of the molecule will take place. So it is the basically the number of the molecules which are basically affecting the water concentration, not their chemical composition. It will not matter at which type of the molecule is actually moving. On the other hand, if the molecule that is ionized in solution, it will decrease the water concentration in proportion to the number of the ions produced. For example, in the previous example, we have observed that glucose is moving, and glucose is moving is in a molecular form. So if we take another molecule which is polar molecule, and that ionized in the solution, so it will decrease the water concentration in proportion to the number of the ions that will be formed by that particular solute. For example, if we take one molecule of the sodium chloride, it means sodium chloride, it will dissociate into sodium ion as well as chloride ion. In solution, it will give rise to the one molecule of the sodium ion and one molecule of the chloride ion. So overall, it will produce two molecules of the solute particle, one molecule of the sodium as well as one molecule of the chloride. So in combined form, it means two molecules of the solute particles, they are being produced by this sodium chloride, one molecule of the sodium chloride in a solution. So it means the water concentration will be lowered by 2 as compared to 1, or as when we compare it with the one molecule of the glucose. So it means one molecule of the glucose and one molecule of the sodium chloride, they will have different effect on the water concentration. One molecule of the glucose will decrease the water concentration by one molecule, but one molecule of the sodium chloride, because of its ionic nature, it will dissociate into two different ions. So one molecule of the sodium chloride will decrease the water concentration by 2 as compared to the one molecule of the glucose, which will decrease the water concentration by 1. So similarly, if we talk about some other polar molecule, for example, one molecule of the magnesium chloride, it will lowers the water concentration by 3 times as much as one molecules of the glucose solution. For example, when the magnesium chloride is added into the water, it will dissociate into one magnesium ion and 2 chloride ion. So in cumulative way, the 3 molecules of the solute, they will be added to the water solution. So this one molecule of the magnesium chloride will lower the water concentration 3 times as compared to the one molecule of the glucose solution. Have you got my point? Is it clear to all of you?
Yes, sir.
Okay. So water concentration in solution, it actually depends upon the number of the solute particles that are being added to the water solution. So we will have concentration terms, or the concentration of the solute particles in a solution regardless of their chemical composition. So we will normally measure the concentration of the solute, whether there is one solute particle solute particle, 3 solute particle, and we will have nothing to do with their chemical composition. Whether one molecule of the glucose, one molecule of the ammonia, one molecule of the amino acid, all of them, they will have the same impact on decreasing the water concentration. So the total solute concentration of the solution is called as osmolarity. This is the term osmolarity, the total number of the solute particle or total solute concentration in a solution or of a solution will be called as osmolarity, and 1 osmole is equal to 1 molecule of the solute particle. For example, when we add 1 molecule of the glucose to the liter of the water solution, it means that the osmolarity of the glucose molecule in that water solution will be 1 osmole. So 1 molar solution of the glucose or 1 molecular solution of the 1 molar solution of the glucose having a concentration of 1 osmole per liter, mean 1 molecule of the glucose added to the liter of the solution, that is called 1 osmole. Whereas when we talk about the 1 molar solution of the sodium chloride, because of its ionic nature, it will dissociate into sodium and chloride ion. So overall the osmolarity of this 1 molar sodium chloride solution will be 2. So it will have 2 osmole of solute per liter of the solution. So liter of the solution which is containing 1 molecule of the glucose and 1 molecule of the sodium chloride, it will have total osmolarity that will be equal to 3 osmole. So the total osmolarity in a solution which is having 1 molecule of the glucose and 1 molecule of the sodium chloride, that will be 3 osmole. So any solution which is having osmolarity of the 3 osmole, it may contain 1 molecule of the glucose and 1 molecule of the sodium chloride, or it can also have 3 molecule of the glucose, or it can have 1.5 molecule of the sodium chloride, or any other combination of the solute, as long as the total solute concentration is 3. So you can simply calculate the osmolarity of the solution in which we have either 3 molecule of the glucose, the osmolarity will be 3 osmole, or we have 1 molecule of the glucose and 1 molecule of the sodium chloride, again the osmolarity will be 3, or we have 1.5 molecule of the sodium chloride, it will also have the total osmolarity of 3 osmole per liter. So osmolarity basically refers to the concentration of the solute particle. So it is also important to know that water concentration in the solution, osmolarity will also determine the water concentration, because it is directly related to the water concentration as well. How? When we will increase the osmolarity, mean number of the solute particles, when their number is increased in the solution, the osmolarity of the water or the water concentration will automatically decrease there. So that's how we can say that osmolarity, number one, it determines basically it shows the number of the solute particles which are added to the solution. At the same time, it is also having an impact on the water concentration as well, mean increase in the solute particle will decrease the water concentration, or it will lower the water concentration. So concentration of the water in any two solution having the same osmolarity is the same, since the total number of the solute particles per unit volume is the same. So if the two solution, let's say we have two solution, solution A and solution B, and both of them are having the osmolarity that is equal to 3 osmole per liter. So water concentration in both of those solution will be 52.5 molar, because they are having the same osmolarity or same solute concentration. So let's now apply this principle to the water concentration. And we will also study the diffusion of the water across the membrane. So in the next okay, we have already discussed this in this figure, that we have two compartments. This is compartment 1 and compartment 2, and initially there is high concentration of the solute and low concentration of the solute in the compartment 1. So solute will move from higher to lower concentration, and water will move from its higher concentration to lower concentration. Mean water movement will be from compartment 1 to 2, and solute movement will be from compartment 2 to compartment 1. Okay, we already have discussed this. So at the equilibrium stage, or if we talk about the net movement, so net diffusion of the water from higher concentration mean from compartment 1 to compartment 2, and it will lower the concentration in compartment 2, and the solute in the opposite direction means solute will move from compartment 2 to compartment 1, and water will move from compartment 1 to compartment 2. And when the diffusion equilibrium is reached, the two compartments will have identical solute and water concentration, mean we will have the 3 osmol solute concentration, and we will have 52.5 molar water concentration, and 1 mole of water will have diffused from compartment 1 to compartment 2, and 1 mole of solute will have diffused from compartment 2 to compartment 1. Since 1 mole of solute replace 1 mole of water in the compartment 1, and hence overall volume of the either compartment, there will be no change. Concentration will be changed, uh, but the volume will remain same. The volume in all these cases will be 1 liter, because as I have told you that if one molecule of the water that has moved from compartment 1 to compartment 2, it means now there will be 999 molecules, but at the same time from compartment 2 to compartment 1, due to the movement of this solute particle, one molecule of the solute will be added to this compartment 1, and hence the total volume of the solution in both compartments will remain same. So that's how the water is moving. Okay, and now let's take another example, and now we replace the membrane with the help of one which is, please stay connected. Let me check something. Okay, let me share another diagram with you, in which we will have a clear idea. लो वालेकुम सलाम जी, शुक्र है। Sorry for inconvenience. Can you see the slide? Can you see the slide on your screen? Are you there?
Yes, sir.
Okay, this is what I wanted to share with you. That in another example, initially in the previous figure, we have said that the membrane was permeable to both water as well as solute. But in this case, here you can see that this membrane is only permeable to the water, whereas it is impermeable to the solute particle. And in the same way, the water, because it is having higher concentration in the compartment 1, and it is having lower concentration in the compartment 2, so water will move from higher concentration to lower concentration, mean from compartment 1 to compartment 2. But on according to the diffusion rule, the solute in this case, it should have moved from compartment 2 to compartment 1, because solute is having higher concentration in compartment 2 and it is having lower concentration in compartment 1. But because of the impermeable nature, the solute particle will not be able to cross through this moment. So now what will happen? So moment, how the equilibrium in this case will be achieved. Here now you can see that the water molecule that has moved from compartment 1 to compartment 2, and the volume has increased in the compartment 2. Now the solute concentration, the high concentration of the solute was diluted with the more movement of the water molecule from compartment 1 to compartment 2, as a result of which now there will be effect on the volume of the solution as well. Initially there was no effect on the volume of the solution, because the molecules of the solute that were moved from compartment 2 to compartment 1, they were replaced by the molecules of the water that were moving from compartment 1 to compartment 2. But in this case, no solute particle, they are moving from compartment 2 to compartment 1, but the water molecules are moving, and they will start their movement unless until the solute is diluted enough so that the two compartments will have same solute concentration. So in this case, the volume of the compartment 2 will be increased because of the more movement of the water molecule, and the volume of the compartment 1 will be decreased because more water molecule they have moved from compartment 1 to compartment 2. Now the solute concentration will be at equilibrium stage. The solute concentration will be same in both compartment. It will be 3 osmol per liter. The water concentration will again be same in both compartment, but the volume of the two compartment will be decreased, will be different. Compartment 1 will have the more. Yes, please. Have you got the point? If there is any confusion, you can ask, please. Okay. So in this case, the volume of the compartment 1 will be decreased, and the volume of the compartment 2 will be increased. So this is what we have discussed, or what we have studied in the figure, that if the membrane is replaced by one that is permeable to the water, but that is impermeable to the solute, the same concentration of the solute and water will be reached at equilibrium stage, but now the volume of the two compartments will be changed. As according to the diffusion rule, water will move from compartment 1 to compartment 2, but there will be no solute diffusion in the opposite direction, because the membrane is impermeable to the solute particle. So water will continue to move unless until the both compartment they have equal water concentration as well as equal solute concentration. So solute concentration in the compartment 2 decreases, as it is diluted by the incoming water, and the solute in compartment 1 becomes more concentrated, because water is actually moving from compartment 1 to compartment 2. So when the water reaches the diffusion equilibrium, the osmolarities of the compartment will be equal, mean the solute concentration and the water concentration in both compartments will be equal, but there will be a difference of the volume in the two compartments at the equilibrium stage. So water will pass from compartment 1 to compartment 2, and compartment 2 will have higher volume. There will be increase in volume of the water as compared to the compartment 1, and there will be decrease in. So 1/3 volume of the compartment 1 will be increased, and 1/3 volume of the compartment 2 will be increased, and 1/3 volume of the compartment 1 will be decreased. So it means that these two compartments they were expendable, mean net transfer of the water that does not have any impact on the structure of the cell, mean that was the elastic cell, and the moment of the water molecule, it was having no abuse effect on the elasticity or the integrity of the structure. But sometime if the walls of the compartment 2, if they are not expandable, mean they are not elastic, then the movement of the water in compartment 2 will raise the pressure in the compartment 2, and when the pressure is increased, no further movement of the water will be allowed. This is what we can call it as the osmotic pressure. You are all familiar with this term. So the movement of the water in compartment 2, it can be prevented by application of pressure to the compartment 2, and this pressure is called osmotic pressure. So when the solution is containing non-penetrate solute, it is separated from the pure water by a membrane, and this membrane will exert a sort of the pressure that must be applied to the solution to prevent the net flow of the water into the solution is termed as osmotic pressure of the solution. Mean if the membrane is, although membrane is permeable, but the membrane is not elastic. So when a certain number of the water molecule they have entered into that particular solution, the membrane, the wall of that particular cell will exert a pressure, and it will prevent the further entry of the water molecule into that cell. This type of the pressure will be called as osmotic pressure. So the greater the osmolarity of the solution, the greater is the osmotic pressure. So it is very much clear that when there is high concentration of the solute, the water will move to dilute that solute particle, and when the water will move, definitely the wall of that particular cell will have high pressure, high osmotic pressure, and it means that the osmotic pressure it does not push water molecule into the solution. Mean it is actually the what we can call it as it is actually the resistant force that prevent the further entry of the water molecule into solution when the inside of the cell become fully saturated with the water molecule. So it is basically the amount of the pressure that would have to be applied to the solution to prevent the net flow of the water into the solution. And like osmolarity, the osmotic pressure of a solution is measure of the solution's water concentration. Mean if there is high concentration of the water, the low high concentration of the solute, automatically there will be the low concentration of the water, and more water will move into that solution. So if we have high concentration of the solute or high osmolarity of the solute or low concentration of the water, in both of the cases the osmotic pressure will high. Have you got my point? If we have high concentration of the solute, means solute जब ज़्यादा होगा तो ज़ाहिर है वाटर की concentration क्या होगी, कम होगी, और जब वाटर की concentration कम होगी तो ज़्यादा वाटर मूव करेगा ताकि उस solute को क्या करे, dilute करे to reach the equilibrium stage, और जब वाटर की concentration कम होगी तो it means ज़्यादा वाटर मूव करेगा, और एक पॉइंट ऐसा आएगा कि osmotic pressure जो है फर्दर इसकी एंट्री को क्या करेगा, प्रिवेंट करेगा. ठीक है. Another important point is extracellular osmolarity and cell volume. Mean what will be the impact of the osmolarity or the solute concentration on the volume of the cell. Now we can apply the principle which we have learned about the osmosis to the cell, and For example, uh, if we talk about the intracellular and extracellular fluid, as all of you know that both of them, they are having the water, and the cells are surrounded by a membrane that is very permeable to the water but impermeable to many substances. For example, non-penetrating solutes, those solutes to which the plasma membrane is impermeable. 85% of the extracellular solute particles, when we talk about the extracellular solute particle, they are sodium and chloride ions. And as all of you know that membrane is very much permeable to these ions. They can simply diffuse across a membrane with the help of channels, and they can enter into the cell during the active transport. So plasma membrane contains sodium potassium ATPase pump that actively move sodium ions outside of the cell. So the sodium which move from outside to the inside during the process of diffusion with the help of sodium channels or the potassium channel, that sodium is pumped back by the help of sodium potassium ATPase pump. Class के बाद that is basically pumped out with the help of sodium potassium ATPase pump. So it seems that this plasma membrane is impermeable to the sodium ion, although in real sense it is not impermeable. It is permitting the movement of the sodium ion from higher sodium concentration to lower sodium concentration. Means sodium are moving across the membrane from their higher concentration to lower concentration, but the sodium ion that has moved via the process of diffusion, they will be moved back, they will be transferred back with the help of sodium potassium ATPase pump via the process of active transport. So when the secondary active transport mechanism is there, membrane potential, it will move chloride ion, and same is the case with the chloride ion as well. As all of you know that the chloride, they are having higher concentration on the outer side and they are having lower concentration in the inside, and during the process of diffusion, chloride will simply move through the help of chloride, with the help of chloride channel, from their higher concentration to the lower concentration. But when the active transport mechanism and secondary active transport mechanism is operative there, it will move the chloride ion back from inside of the cell to the outside with the help of chloride ions, with the help of chloride pumps. So it means the membrane is basically behaving as non-penetrating membrane or impermeable membrane to these solute. So inside the cells, the major solute particles now which are left behind are the potassium ions and number of the organic solutes we will discuss. And most of these organic solutes, they are polar molecule, and they are unable to move across the membrane. So if we talk about the potassium ion, they can diffuse out of the cell. As all of you know that the potassium, they are having the higher concentration on the inside and lower concentration on the outer side. But when the potassium ion, through the process of diffusion, they are moving from inside to the outside, immediately when the active transport mechanism is operative there, those potassium ion are pumped back from outside to inside, from their lower concentration to their higher concentration with the help of sodium potassium ATPase pump. So as in, if we talk about the net effect, as with extracellular sodium and chloride, same is the with the potassium ion. Mean, although in real sense the membrane is permeable to potassium ion, it is permeable to the sodium ion, it is permeable to the chloride ion, but the mechanism which are operative, initially the mechanism of diffusion and later the mechanism of the active transport, due to these operative mechanism inside the cell, it seems that the membrane is impermeable to these solute particles. The sodium and chloride outside the cells and potassium in organic solute inside the cells, they are actually behaving as the non-penetrating solute on the two sides of the plasma membrane. So the osmolarity of the extracellular fluid, it is about 3 molar osmol. Since water can diffuse across the membrane, the water in the intracellular and extracellular fluid, it will reach to the diffusion equilibrium. At equilibrium, the osmolarities of the intracellular and extracellular fluid, it should be same. It means it should be 300 molar osmol or osmolar. This is the osmolarity. So the changes in the extracellular osmolarity, ultimately it can cause the cell to shrink or swell. mean when there is change in the extracellular osmolarity, mean if we change the solute concentration outside the cell, or if we increase the solute concentration outside the cell, it means the extracellular side, it means there will be definite movement of the water. ठीक है, वाटर मूवमेंट क्या होगी, वो बढ़ेगी. अगर हम आउटसाइड द सेल जो है वो उसको चेंज करते हैं तो वाटर जो है वो आउटसाइड से इनसाइड से बाहर आएगा ताकि उसको क्या करे, उसको डाइल्यूट करे. अगर हमने बायस ऑस्मोलरिटी सल्यूट कंसंट्रेशन इंक्रीज की है और अगर हमने सल्यूट कंसंट्रेशन जो है वो डिक्रीज की है तो फिर उसको इक्विलिब्रियम स्टेज पहुंचाने के लिए वाटर क्या करेगा, बाहर से अंदर की तरफ मूव करेगा ताकि अंदर और बाहर जो है वो सल्यूट कंसंट्रेशन क्या हो जाए, वो सेम हो जाए. सो इफ द वाटर इज मूविंग आउटसाइड, it means the cell will shrink, and if the water is moving inside, it means the cell will swallow. Cell जो है वो क्या करेगा, वो जो है उसमें प्रेशर जो है वो बढ़ेगा. So if the cells are placed in a solution of non-penetrating solute having an osmolarity of 300 molar osmol, they will neither swell nor shrink since the water concentration in the intra and extracellular fluid are the same. यानी नॉर्मल हमने ये कह दिया कि ऑस्मोलरिटी कितनी होती है, 300 मोलर ऑस्मोल है. तो अगर हम इस सेल को ऐसे सॉल्यूशन में रखते हैं जिसकी ऑलरेडी जो है वो ये सेम है, तो इसको हम क्या कहते हैं, आइसो ऑस्मोटिक सॉल्यूशन. दिस विल बी कॉल्ड एज आइसोटोनिक सॉल्यूशन एज वेल. यू कैन आल्सो कॉल इट एज आइसोटोनिक सॉल्यूशन. तो इसमें कोई जो है वो चेंज नहीं आएगी, नाइदर इन द एक्स्ट्रासेलुलर इन द इंट्रासेलुलर फ्लूइड solute will neither leave or enter into the solution. ठीक है, इनको हम क्या कहते हैं, these are called isotonic. Such type of the solutions are called isotonic. They are having the same concentration of the non-penetrating solute as the normal extracellular fluid. If we have the solution which are having less than 300 mol of non-penetrating solute, that will be called as hypotonic solution. They will, in that case, because of the low concentration on the extracellular side of the solute, the water will move from extracellular side to the inside of the cell, and cell will start to swell because water will diffuse into the cells from its higher concentration in the extracellular fluid. So it means that type of the solution will be called as hypotonic. And if the solution which are having greater concentration of the solute, mean greater than the 300 molar osmol, it means the solute concentration is high. So what will happen? In that case, the water from inside the cell will move to the outside to dilute the solute concentration. In that case, cell will shrink, the water volume will decrease in the cell, and that particular type of the cell will be called as hypertonic. It will cause the cell to shrink as water diffuses outside of the cells. So concentration of the non-penetrating solute in a solution, not the total osmolarity, it will determine the tonicity. Mean hypotonic, isotonic, or hypertonic solution, the tonicity will depend upon the concentration of the solute. If the solute is in the extracellular side is having 300 molar osmolarity, it means it is having the same solute concentration as that of the normal cell. So there will be no net movement. That will be called as isotonic. If we extracellular side, if we have lower concentration of the solute, mean less than 300 molar osmol, it means the solute is having lower concentration, water is having higher concentration in the cellular side, so water will move from extracellular side to inside the cell, and inside the cell will start to swell because of the increase of the water volume. This will be called as hypertonic. And in case of hypotonic, if we have solute concentration that is higher than 300 molar osmol, it means the water from inside of the cell will move outside to dilute the solute concentration which is present on the extracellular side. It means the cell will shrink. So this will be called as hypertonic. So some same term, isoosmotic, hyperosmotic, and hypoosmotic, they can also be used. They simply denote the osmolarity of the solution relative to that of the normal extracellular fluid. And in this case, we will not, in case of hypotonic, hypertonic, or isotonic, we will fix the permeability of the membrane, that the membrane is impermeable to the solute. Solute are actually behaving as non-penetrating. Only water is behaving as the penetrating component in the previous example. But similar type of the terms can also be used, isoosmotic, hyperosmotic, and hypoosmotic. They also will measure the osmolarity of the solution relative to the normal extracellular fluid. But in the isoosmotic, hyperosmotic, or hypoosmotic, we will not count the permeability of the membrane, mean whether the membrane is impermeable to the solute or it is permeable to the, so regardless of the permeability of the membrane, we can calculate the isoosmotic, hypoosmotic or hyperosmotic solution. So this is this here you can also understand all these three type of the solution in this diagram. For example, we have normal cell which is having 300 molar. We have normal cell which is having 300 molar osmolarity, and these are the three type of the cells. Initially, if this cell is placed in a solution which is having 300 molar osmol and solute is non-penetrating, so there will be no movement because solute concentration on both sides is same. But if the cell is placed in a solution which is having high osmolarity, 400 molar osmol, this is the solute concentration on the extracellular side. Now what will happen? The water will move from inside of the cell to dilute this solute particle, and hence the volume of the cell will shrink. This is called hypertonic solution. And in case of hypotonic, if we put this cell in a solution which is having lower solute concentration, mean less than 300 molar osmol, in this case, because water is high and solute is having lower concentration, so to reach the equilibrium stage or to dilute this or to increase the solute concentration, water will move from outside to the inside, and hence inside the cell volume will be increased. That will be called as hypotonic solution. Cell will swell. So the two set of the terms which we have used, hypertonic, hypotonic and isotonic, and similarly hyperosmotic, hypoosmotic or isoosmotic, they are not synonymous terms. They can be used in different ways. For example, 1 liter of the solution which is having 300 molar osmol of non-penetrating sodium chloride and 100 molar osmol of urea, which is actually penetrating across the membrane, they will have total osmolarity which will be equal to 400 molar osmol, and it will be hyperosmotic. Means in this case we are not taking into the consideration the permeability of the membrane. Mean membrane is not impermeable to both of the solute. It is permeable to the urea as well as it is impermeable to sodium chloride. So in this case, this will be called as hyperosmotic, and there will be 400 molar osmol. This will be the concentration of the osmolarity. So at the same time, it can be isotonic as well, because it will produce no change in the equilibrium volume of the cells, which we have already discussed, because it is not permeable to the sodium chloride, whereas it is permeable to the ammonia. So how it will be isotonic solution? 100 molecule or the 100 molar ammonia which have moved from outside to the inside, at the same time that 100 mole can also move from inside to the outside, so there will be no net movement of the urea, because the membrane is permeable to urea as well. So when we take this into the as an isotonic, it can also be called an isotonic solution, because the number of the urea molecules that are moving from extracellular side to the intracellular side, at the same time that is replaced by the movement of the, you can also say that when the solute concentration increase in the inside of the cell, that urea will again start to move from its higher concentration to lower concentration, and at equilibrium stage we will have no net movement. So that's why this can also be called as isotonic solution. So urea will diffuse into the cell and reach the same concentration as the urea in the extracellular solution, and thus both the intracellular and extracellular solution will have the same osmolarity, that will be equal to 400 mole. So there will be no difference in the water concentration across the membrane and no change in the volume. So here in the last table you can also have a clear idea about the terms which we have used: isotonic, hypertonic, hypotonic, and Similarly, isoosmotic, hyperosmotic, and hypoosmotic. So tonicity of the solution, it is very much important in various medical terms. For example, if we talk about the all hypoosmotic solutions, they are also hypotonic, and hyperosmotic solution, they can be hypertonic, isotonic, or hypotonic as well, as we have discussed in previous slide. So one of the major function of the kidney, when we talk about the kidney, it will regulate the excretion of the water in the urine so that the osmolarity of the extracellular fluid remains nearly constant in spite of variation in the salt and water intake and loss. So the kidney is basically it is majorly involved in regulating the water concentration as well as the essential salts and which are required in the body. So kidney will reabsorb those, as all of you know that the nephron portion of the kidney that will reabsorb the essential component as well as the necessary water during the process of excretion, and it will prevent the damage to the cell that can be there due to the shrinkage or due to the swelling. And similarly, if we talk about the tonicity of the solution injected into the body, that is very much important. आपने देखा होगा कि मोस्टली जो है वो सेलाइन यूज करते हैं इंजेक्ट करने के लिए, बॉडी के अंदर कोई भी जो इंजेक्शन है उसको सेलाइन में जो है वो यूज करते हैं. Such solution or the saline solution, they mostly consisting of an isotonic solution of sodium chloride, mean 150 molar osmolarity होती है सोडियम क्लोराइड की, इसको हम जो है वो आइसोटोनिक और सेलाइन सोल्यूशन कहते हैं, और समटाइम 5% डेक्सट्रोज सोल्यूशन जिसको हम जो है वो यूज करते हैं. ठीक है, इंजेक्टिंग ए ड्रग dissolved in such solution, it will not have obvious effect in the cell volume. ठीक है, उसमें जो है वो जैसे लोगों को ड्रिप लगाई जाती है हॉस्पिटल के अंदर, तो वो भी मोस्टली जो है वो सेलाइन में होती है, अदरवाइज दैट कैन हैव इम्पैक्ट ऑन द बॉडी, उसकी वजह से जो है वो स्वेलिंग आ सकती है बॉडी में. ठीक है, सो drug dissolved solution that will not have any effect on the cell volume, they will not change the cell volume, whereas if we inject the drugs in pure water, a hypotonic solution will produce the cell swelling perhaps to the point that plasma membrane in that case can rupture and cell can be destroyed. So here is a comparison. You can have an idea that simple difference between the isotonic and isoosmotic is that both will have the same osmolarity, but regardless of the composition of the membrane, whether the membrane is penetrating or non-penetrating. And in case of hyperosmotic, similarly again we will have 3 molar osmol concentration of the solute, but the membrane permeability will not be counted, whether the membrane is permeable or impermeable. Okay, this is all for today. Is it clear for all of you? If there is any question, you can ask, please.
Yes.
No question?